Hello, this is the section 13.7 lesson. For this section you will need the worksheet Hypothesis Testing Tables, which you should have printed in the previous lesson. Well, let's start off with an observation. Suppose we have 5 males and 5 females seated in a row in this fashion. We've got the females on the left and the males on the right. Here's a question: are they arranged randomly? Well, most people would probably argue no. There's a definite pattern there. All the females on the left, all the males on the right. Well, now let's suppose that they're seated in this way: female, male, etc. Same question: are they arranged randomly? Again, most people would argue no. There's a different pattern there. This section deals with determining if data such as these are arranged in a random order or not. The key idea behind this section is the idea of a run. A run is a sequence of data having the same characteristic. The sequence is preceded and followed by data with a different characteristic or by no data at all. Okay. So let's illustrate this definition here with these examples. When we got all the females on the left, all the males on the right, those 5 females seated together, that's one run. They're preceded by no data, and they're followed by data with a different characteristic. Those 5 males on the right, that's another run. They're preceded by data with a different characteristic, and they're followed by no data at all. So in that example we have 2 runs. In this other example where it's female, male, each person is a run in and of him or herself. That first female has no data before her and data of a different characteristic after her, so that's a run. That first male has data of a different type before and data of a different type after, so that's a run. So each person there's a run, so we have 10 different runs. So in this first example we had only a few runs. The second example we had many runs. So an unusually large or small number of runs contradicts randomness. And that's the idea behind the analysis of the data. If we got a lot of runs or not very many runs at all, we're going to reject the idea of randomness. So the test that we're doing here in this section is what's called the runs test for randomness. We are testing the claim that a sequence of data is arranged randomly. Our data values are of 2 types, like male and female, heads or tails, plus or minus. Our hypotheses for this type of test are that the null is that the data are arranged in a random sequence, and the alternative is that the data are not in a random sequence. Now there's no inequality signs in these hypotheses. Everything is stated in terms of words. But these are always going to be the form of our null and alternative hypotheses. So to do our test here, this is going to be somewhat similar to what we saw in the previous section, in that there's no formulas for the test statistic. All we're going to be doing is counting different types of data elements. So let's let n1 be the number of elements of the first type, n2 number of elements of the second type, and g be the number of runs. Now we're going to do a traditional method to come to our technical conclusion, meaning we're going to compare things to critical values. That comes from table A10, which again is on that worksheet Hypothesis Testing Tables. And from that table we're going to get 2 critical values, a smaller critical value and a larger critical value. Our criteria is that we reject the null hypothesis if g is less than or equal to the smaller critical value, or g is greater than or equal to the larger critical value. And we do not reject the null hypothesis otherwise. So if g is somewhere between that smaller and the larger critical value, we do not reject the null hypothesis. So to illustrate how to read this table, let's look at this example of the females seated to the left and the males on the right. Okay. So for this one we had n1, let's call n1 the number of females, which is 5, n2 the number of males, which is also 5, and then g, the number of runs, was 2. Now we didn't have to let n1 be the number of females and n2 be the number of males. We could have let n1 be the number of males, n2 be the number of females. We would have got the same results in the end. So now to read this table, notice it says value of N1 across on the left, value of N2 across the top. So if we go down to N1 is 5, over to N2 5, we see our two critical values there of 2 and 10. So there's our critical values. Now G is 2. That is indeed less than or equal to the smaller of those two critical values, and so we would reject the null hypothesis. Now the null hypothesis is the statement that the data are arranged randomly, so we're rejecting randomness, and we would conclude that the genders are not arranged randomly. That's just exactly what we concluded earlier. Now the requirements for this type of test are that the sample data are arranged according to some ordering scheme, and number 2, each data value can be categorized into one of 2 separate categories. So our data are not just randomly scattered numbers or males and females. They have to be arranged according to some ordering scheme. In this example, they were arranged according to the way that the people sit. Let's illustrate this with another example. The political parties of the winning candidates for a recent sequence of presidential elections are listed below. Does it appear that we elect Democrat and Republican candidates in a random sequence? So for the first election, Republican won. The second, Republican won. And the third, a Democrat won. Fourth, a Republican won, etc. Now, so here our data are arranged according to the order in which the candidates won. Now we should think of our data as being in one long list as opposed to 2 short lists. And that's important when we calculate the number of runs. So here's our claim, which is the same as the null hypothesis. We elect Democrat and Republican candidates in a random sequence. So the claim and the null hypothesis in this type of test are always the same. It's that things are arranged randomly. Now the alternative hypothesis really isn't terribly important, so we don't even state it. It's simply the statement that they are not in a random sequence. So to do our runs test, let's find N1 and N2. Let's let N1 be the number of Democrats, so we count the number of Ds, which is 14. Let's let N2 be the number of Republicans, so count the number of Rs, and that's 19. Now we could have switched those two around. We could have let N1 be number of Republicans, N2 be the number of Democrats, and we would have been fine. Now next we need to find the number of runs. To do this, it's helpful to write down the sequence of data and then underline the number of runs, or underline each individual run. So those first 2 Republicans constitute a run. Got that Democrat that's surrounded by 2 Republicans, so there's another run. That the Republican is surrounded by 2 Democrats, there's a run. We got a string there of 4 Republicans, that's a run. Now the end of that first row ends with 3 Democrats, and then the next row starts with 2 Democrats. We should think of that as one string of 5 Democrats, or one run of 5 Democrats. So if we count the number of runs that we've underlined there, again remembering that last run in the first row and the first run in the second row are really just one run, we have 15 runs. So there's G. Now we'll get our critical values from table A10 again. There's our values of N1, N2, and G. So if we go down to N1 is 14 and N2 is 19, we get our critical values of 11 and 23. Now note that G is 15, that is between 11 and 23, and so our technical conclusion is that we do not reject the null hypothesis. Now word the final conclusion the same way that we've always done. Now in this case the original claim did not have any equal sign or any other inequality sign. However, the claim and the claim and the null hypothesis are the same, and so we're going to go to the right. Yes, in this type of claim or test we're always going to go to the right. So do we reject the null hypothesis? No, we did not. So there is not sufficient evidence to warrant rejection of the claim that we elect Democrat and Republican candidates in a random sequence. So it appears that we elect Democrats and Republicans in a random sequence, as was originally claimed. One quick comment here is that we are not testing if more Republicans than Democrats win. Here we had 19 Republicans and 14 Democrats, so it appears that more Republicans win, but that's not what we're testing. What we're testing is for randomness in the order in which they win. If we want to test that more Republicans than Democrats win, we could do that, but we'd have to use a different type of test. Alright, let's look at another example of the runs test. Listed below are the high temperatures near the author's home on consecutive days beginning with September 1st. The mean of these high temperatures is 73.8 degrees Fahrenheit. Test for randomness above and below the mean. So on September 1st the temperature was 80, September 2nd the temperature was 77, so on and so forth. As before, our data here are arranged in 3 rows, but we should really think of this as just one long string of numbers as opposed to 3 short strings. So the claim, which is the same as the null hypothesis, is that the temperatures occur in a random sequence above and below the mean. Now in order to use the runs test, we have to break our data down into 2 separate categories. Here we have a lot of different numbers, so we need to break it down into 2 categories. The mean is 73.8. We're testing for randomness above and below the mean. So we're going to categorize each data value as either above the mean or below the mean. And so below each data value we're going to write an A for above the mean or B for below the mean. So our first 4 data values are above the mean, so we write an A. The next 2 are below the mean, so we'll write a B. 80 is above the mean, so on and so forth. So we're really going to be doing our runs test on this sequence of A's and B's. As before, we should think of this data, the string of A's and B's, as one long string as opposed to 3 short strings. Now let's get N1 and N2. Let's let N1 be the number of B's, N2 be the number of A's, which come out to be 16 and 19 just by counting them. Now to find my runs, I need to underline the runs and count them. Okay. So now note at the end of the first row and the beginning of the second row we have this string of A's. Think of that as one long run of 5 A's as opposed to 2 runs. Likewise, we've got a long run of A's at the end of the second row and the beginning of the third row. So if we count the number of runs there, G is equal to 10. Now get our critical values from table A10. Go down to N1 is 16, N2 is 19. We have our critical values there of 12 and 25. Now notice that G is less than or equal to the smaller critical value of 12, and so we reject the null hypothesis. Word our final conclusion in the same way. Remember that this type of claim we always go to the right. Do you reject the null hypothesis? Yes, we did. So there is sufficient evidence to warrant rejection of the claim that temperatures occur randomly below and above the mean. So in other words, the temperatures do not appear to fluctuate randomly below and above the mean. Now let's make a quick observation here. We notice that we've concluded that they're not random, so that means that there's some sort of pattern. Let's see if we can figure out the pattern. Notice at the beginning of the month we had a lot of A's, meaning we were above the mean, but at the end of the month we had a long string of B's. That means that there appears to be a downward trend in temperatures. That's pretty much exactly what we would expect. September you start off warm and you get colder. So that's it for this section. The homework is section 13.7.